For decades, the hunt for life beyond Earth resembled listening to static, faint murmurs from distant stars that never quite coalesced into a clear message. Every promising signal eventually collapsed under scrutiny. Every Earth-like planet turned out to be just close enough to disappoint. But then, the James Webb Space Telescope saw something different. It saw something disturbingly precise. This wasn't a vague hint. It was a convergence of data so statistically overwhelming that it forced scientists to abandon cautious language. This time, Webb didn't just detect an atmosphere, water, or a favorable temperature range. It detected a planetary environment where almost every known requirement for life aligns simultaneously, stacking probability upon probability until the odds approach a staggering 99.9%. What makes this discovery so unsettling is not just the strength of the evidence, but its source. It didn't come from a science fiction corner of the galaxy or an unreachable star system, but from places astronomers thought they already understood. Worlds we had categorized, labeled, and often completely dismissed are now being re-examined under Webb's unforgiving gaze. As each layer is peeled back, a pattern emerges, one suggesting we have been surrounded by habitable environments far longer than we realized. If Webb is right, humanity's biggest mistake was assuming life would announce itself loudly. Instead, it may have been hiding quietly, waiting for us to finally build the eyes capable of seeing it. When James Webb's data began pointing towards Ceres, many scientists were caught completely off guard. For most of modern astronomy, Ceres was treated merely as an oversized asteroid, a leftover building block from planet formation, interesting geologically but irrelevant to the search for life. Webb changed that narrative almost overnight. Spectral analysis revealed extensive deposits of salts and hydrated minerals spread across its surface. The unmistakable fingerprints of liquid water interacting with rock, not briefly, but persistently over geological timescales. What lies beneath those salts is where the story becomes extraordinary. Data now strongly supports the existence of a vast subsurface ocean. This is not a frozen relic, but a briny, chemically active sea trapped beneath a thick crust of ice and rock. This ocean would be protected from cosmic impacts, temperature swings, and radiation, creating a stable environment remarkably similar to Earth's deep oceans, where life thrives without sunlight. Even more compelling are signs of ancient, and possibly ongoing, hydrothermal activity, the same energy source that fuels ecosystems around Earth's seafloor vents. In other words, Ceres checks boxes that scientists once believed could only be satisfied on distant exoplanets. Liquid water, mineral interaction, chemical energy, long-term stability. The analogy is unsettlingly simple. If Earth's deepest oceans can host life without sunlight, why would Ceres be any different? Webb forces us to confront the humbling possibility that one of the most promising habitats for life has been orbiting quietly between Mars and Jupiter this entire time, overlooked simply because we assumed we already knew its story. While Ceres shocked scientists by revealing what it hides beneath its surface, another candidate emerged by doing the opposite, by refusing to be seen at all. Across the outer solar system, objects in the Kuiper Belt behave in ways that defy randomness. Their orbits are stretched, tilted, and mysteriously aligned, as if something massive is shepherding them from the darkness. This invisible architect has been named Planet Y. Planet Y is not detected through light, but through gravity, the most honest force in the universe. Calculations suggest a world roughly Earth-sized, orbiting at extreme distances between 100 and 200 astronomical units from the Sun. At that range, sunlight is little more than a rumor, and the planet would appear almost invisible against the cosmic background. But invisible does not mean insignificant. Its gravitational influence is written across the solar system like fingerprints at a crime scene. If Planet Y exists, and the evidence continues to mount, it forces a radical shift in how we define our planetary neighborhood. A hidden Earth mass world, potentially possessing internal heat, subsurface layers, and long-term stability, quietly reshaping the orbits of distant objects while remaining undetected for centuries. Webb sensitivity now brings the first realistic chance of spotting it directly. If confirmed, it would mean our own solar system is far from fully mapped. The unsettling implication is that entire worlds can exist in stable silence, unseen yet dynamically alive. When Webb turned toward the TRAPPIST-1 system, expectations were already high, yet reality exceeded them in a way few anticipated. 7 Earth-sized planets orbiting an ultra-cool star, so closely packed that the system resembles cosmic clockwork, with each world influencing the others via gravitational precision. What Webb revealed was not just planetary diversity, but repetition. Multiple planets show independent signs of conditions that could support liquid water. Several of these worlds appear capable of sustaining global oceans, not shallow seas, but deep, planet-wide reservoirs that could remain stable for billions of years. TRAPPIST-1 stands out as a particularly compelling candidate, showing signs of a balanced atmosphere capable of retaining moisture and heat, while neighboring planets may host vast water layers beneath their surfaces. Imagine standing on one of these worlds and seeing another potentially habitable planet looming in the sky, close enough to feel almost reachable. This system challenges one of our deepest assumptions, that habitable planets are rare accidents. TRAPPIST-1 suggests the opposite, that once the right conditions exist, nature may produce not one living world, but several at once. Webb transforms TRAPPIST-1 from a curiosity into a laboratory, a place where scientists can study how life-supporting environments emerge, interact, and possibly influence each other across planetary boundaries. K2-18b may be the most disruptive discovery of them all because it refuses to resemble Earth. Classified as a Hycean world, it likely possesses a deep global ocean buried beneath a thick, hydrogen-rich atmosphere, a configuration once dismissed as inhospitable. Webb's observations shattered that assumption. The telescope detected water vapor, carbon-bearing molecules, and atmospheric conditions that could allow warm, stable layers far below the cloud tops, precisely where liquid water could persist. This is where the analogy becomes powerful. If Earth is a coastal planet bathed in sunlight, K2-18b is a pressure cooker ocean, sealed, insulated, and protected, where chemistry can evolve slowly but relentlessly. Life here would rely not on sunlight, but on chemical gradients and internal heat, similar to ecosystems near Earth's hydrothermal vents but scaled to an entire planet. The possibility that complex molecules exist within this environment pushes K2-18b dangerously close to biological relevance. What K2-18b teaches us is that habitability is not narrow or fragile. Life does not demand blue skies or familiar landscapes. It demands energy, stability, and chemistry. Webb shows that these ingredients can exist in places we once considered alien beyond usefulness. This single planet expands the catalog of potentially living worlds from dozens to thousands. Proxima b is unsettling for one simple reason. It is close. Uncomfortably close. Orbiting the nearest star to our Sun, this planet has tempted scientists for years. But James Webb has elevated that temptation into something far more serious. Proxima b sits squarely within its star's habitable zone, a region where liquid water could exist on the surface. While its red dwarf star is volatile, Webb's refined observations suggest that Proxima b may possess mechanisms to retain an atmosphere far longer than previously believed. Think of Proxima b as a candle in a storm. The stellar flares are frequent, unpredictable, and violent. Yet, the planet may still be holding on, protected by a dense atmosphere or magnetic field acting like armor. If liquid water exists there, it is likely distributed in stable regions, perhaps in subsurface reservoirs or oceans shielded from radiation. This transforms Proxima b from a risky bet into a calculated one. A world that survives not because conditions are gentle, but because it has adapted to hostility. What makes Proxima b so powerful in the search for life is proximity. Signals from this world take just over 4 years to reach us, a cosmic whisper compared to the silence of distant galaxies. If life exists there, even if microbial, it would mean that biology is not an exotic accident, but something that emerges readily, even under pressure, even next door. At first glance, WASP 39b seems like an odd choice in a discussion about life. It is a gas giant, far too large, far too hot, and completely inhospitable on the surface. But James Webb revealed something unprecedented here, not habitability, but clarity. For the first time, scientists obtained an extraordinarily detailed chemical breakdown of an exoplanet's atmosphere, detecting water vapor, carbon dioxide, sulfur compounds, and complex atmospheric structures with stunning precision. Why does this matter for life? Because WASP 39b is proof that Webb can read the atmospheric fingerprints of distant worlds with surgical accuracy. It is like calibrating a microphone using a loudspeaker before listening for a whisper. If Webb can detect subtle chemical imbalances here, then identifying biosignatures on cooler, smaller planets becomes far more realistic. WASP 39b is not a home for life, but it is a technological milestone, a demonstration that we now possess the tools required to detect life indirectly through chemistry alone. Teegarden b does not scream for attention, and that may be exactly why it matters so much. Orbiting an ultra-cool red dwarf, this Earth-sized planet receives a level of stellar energy strikingly similar to what Earth receives from the Sun. Webb-era models suggest that if Teegarden b has retained an atmosphere, it could support stable surface temperatures, allowing liquid water to exist for billions of years without dramatic extremes. What sets Teegarden b apart is stability. Unlike more violent red dwarf systems, its star appears relatively calm, offering a long-term environment where chemistry can evolve consistently and slowly. This is the kind of patience life prefers, not explosive beginnings but quiet persistence. If Earth is a planet that learned to balance chaos and calm, Teegarden b may represent a world where calm came first. In terms of probability, Teegarden b quietly increases the odds. It suggests that Earth-like conditions do not require rare stellar configurations, only balance, time, and endurance. TOI 700 feels familiar in a way that is hard to ignore. This system hosts multiple planets, one of which orbits comfortably within the habitable zone, with size and energy levels remarkably close to Earth's. James Webb observations indicate that this planet may possess a long-term climate balance and a stable atmosphere, the two ingredients most critical for sustaining liquid water over geological timescales. What makes TOI 700 so compelling is how ordinary it appears. In astronomy, ordinary is revolutionary. A planet with Earth-like proportions, orbital stability, and a calm star allows climate systems to persist rather than collapse. It feels less like a cosmic experiment and more like a replay of something we recognize. This resemblance forces an uncomfortable realization. If systems like TOI 700 are common, then environments suitable for life may be far more widespread than we ever dared to assume. TOI 700 doesn't shock through extremes. It persuades through consistency. At first glance, proximity feels like destiny. Proxima b sits just over 4 light-years away, practically next door on a cosmic scale, while worlds like TOI 700 or the TRAPPIST, one planets lie far deeper in space. Instinctively, we want to believe the closest planet offers the best chance for life. But Webb's data quietly dismantles that assumption. Proxima b is battered by stellar flares. Its environment is unstable and aggressive, a place where life would need to fight constantly just to persist. Compare that to the calm consistency suggested by TOI 700's habitable zone planet, orbiting a quieter star, or to the tightly choreographed worlds of TRAPPIST, one where stability emerges from balance. Webb reveals that distance is irrelevant. What matters is not how close a planet is to us, but how long its environment can remain stable without being reset by catastrophe. In that comparison, proximity loses its advantage, and endurance becomes the real currency of habitability. Atmospheres are where planets reveal their true character. K2-18b wears its atmosphere like armor, a thick, hydrogen-rich envelope capable of insulating a deep global ocean from cosmic chaos. It is the opposite of Earth-like, yet potentially more forgiving to life. Meanwhile, Proxima B's atmosphere, if it exists, must survive relentless stellar activity, making it a fragile skin constantly at risk of being stripped away. Then enters WASP 39b, not as a habitable world, but as a benchmark. Its atmosphere is so clearly readable by Webb that it proves beyond doubt that we could dissect alien skies molecule by molecule. When these worlds are viewed individually, each feels like an exception. Together, they form a pattern impossible to ignore. Ceres shows habitable environments can exist without sunlight. K2-18b proves thick atmospheres and deep oceans may be more life-friendly than Earth-like surfaces. TRAPPIST-1 demonstrates that multiple habitable candidates can exist side by side. TOI 700 shows quiet, Earth-sized systems are not rare. WASP 39b confirms we can read alien chemistry with confidence. Proxima b reminds us that even hostile worlds may endure. This is no longer a scattered collection of curiosities. It is a gradient of habitability spanning from hidden oceans to exposed atmospheres, from violent stars to calm ones. Webb reveals that life does not require a single perfect recipe, only a range of viable ones. And when so many different planets satisfy different parts of that recipe, the uncomfortable implication is that the universe may be biased toward life, not indifferent to it. For years, planets like Ceres, Proxima b, TRAPPIST-1, K2-18b, and Teegarden b were treated as individual curiosities, fascinating but isolated. James Webb makes that separation impossible. When viewed together, something unsettling becomes clear. There are variations of the same theme repeating under different conditions. One of the most powerful insights from comparing these worlds is that they take radically different paths toward the same destination. Some protect their oceans under ice, like Ceres. Others hide them under kilometers of atmosphere, like K2-18b. Some orbit violent stars and endure, like Proxima b. Others enjoy calm, patient stellar environments, like Teegarden b and TOI 700. It is like watching evolution try different strategies to reach the same goal: shielding, insulation, redundancy, proximity, distance. Webb shows that life does not depend on one narrow scenario. It depends on flexibility. If one path fails, another remains viable. This is not fragility. This is robustness built into planetary systems themselves. At some point, accumulation becomes overwhelming. One planet with water is intriguing. 2 is suggestive. A dozen across different systems, stars, sizes, and architectures pushes us past a statistical breaking point. James Webb doesn't need to detect life directly to change history. It only needs to show that the conditions for life are not rare, not fragile, and not short-lived. This is where the infamous 99.9% stops sounding sensational and starts sounding conservative. It is no longer a claim about a single planet, but about a planetary population. Webb is not pointing at one world and saying here. It is gesturing broadly and saying, everywhere like this. Before Webb, humanity asked whether life could exist elsewhere. After Webb, the more honest question becomes how often it does. This collection of worlds represents the transition from possibility to expectation. This is the threshold moment where the universe stops looking empty and starts looking inhabited, even if we have not yet seen a signal or heard a voice. The realization settles firmly. The conditions that produce life on Earth are not unique or sacred. They are reproducible. And if they are reproducible, then life is not an anomaly. It is a consequence. James Webb has not answered the biggest question humanity has ever asked. but has cornered it. And once a question is cornered, the answer is only a matter of time. History will likely remember this moment not as the day we discovered alien life, but as the day we realized how inevitable it might be. The universe no longer feels silent, it feels patient. And now, the responsibility shifts to us. Because if life is common, if we are not unique, then the next discovery will not just be scientific. It will be cultural, philosophical, and deeply personal. So stay with this journey. Subscribe, turn on notifications, and keep looking up, because the question that defined humanity for thousands of years is closer than ever to being answered. And when it is, everything we know about our place in the universe will change forever. I'd love to hear what you think about this, so drop a comment below. If you enjoyed our conversation today, please share this video and subscribe to help the channel grow. Every bit of support counts.